So in this video, we're going to design a PID controller for GC, which is this block in the diagram. And we want to design it such that we get a settling time of 0.1 seconds, an overshoot of 5%, and we want no steady state error for a step input. So for this video, I'm going to follow through the process that I outlined in the recap video for designing PID controllers. That's this one here. So we'll start with the first step, which is deciding on where our desired pole locations need to be based on the criteria that we've got. So we've got three different criteria that we need to meet. The first one we're told is that we're aiming for a settling time of 0.1 seconds. We've then got this overshoot requirement, we're aiming for 5%, and we want to have a steady state error of 0 for a step input. So from this, we should be able to work out what zeta, our damping ratio, needs to be, and our omega n, natural frequency, needs to be as well. So I'm going to start with dealing with the zeta, okay? And we know that we can calculate this when we have a percent overshoot with the following equation. So if we substitute in our 5%, so it's going to be 5 in here for the 2% overshoots, what we find is that our damping ratio needs to be 0.69. So now I should be able to figure out what omega n needs to be based on this settling time requirement. And we have this equation to work with, where we know the settling time is equal to, I should write approximately, 4 divided by omega n times zeta. So if we sub into this, we have that our settling time needs to be 0.1. Omega n is what we're trying to determine, and we've already said this needs to be 0.69. So we find out that our natural frequency needs to be about 57.97 radians per second. So from this, we should be able to figure out our desired pole locations. And for a second order system, which is what we've got here, our desired poles can be found from this general equation. Like so. So if we substitute omega n in here and zeta in here, what we end up with is this is about negative 40 plus or minus this part here simplifies to about 42, and I is our imaginary number. So this is where our poles need to be if we want to be able to meet this two criteria here. So the last criteria we have is with respect to the steady state error. So we should be able to have a look at whether designing a PID controller will impact on our steady state error. So I'm going to do this by looking at our system type and then our error constants corresponding to that system type. So remember that if you want to work out the type of system you have, you need to know your open loop transfer function. So your open loop transfer function is the one where you don't consider the feedback, so it's just going to be the top line of this equation. Block diagram, I should probably say. So ours is just going to be this block multiplied by this block. So I can write that as 10 GC on S plus 1, S plus 2. Now we're told that we're designing for a PID controller. So that means that we know the form that GC, our controller transfer function, should take. So when we design it, we're going to be aiming for something of the form like this. Okay, so we're going to introduce 2 zeros into the system and 1 pole into the system at 0. So if I put this into our open loop transfer function, I'm going to find that it's 10k s plus a s plus b on s, s plus 1, s plus 2. So now we should be able to figure out the system type that we have. And what we're looking for is the number of S's that we have on the bottom line, which are on their own. So in this case, we've got one S on its own out the front. One S. So that means that we have a type 1 system. Alright, so let's remember that we have a type 1 system once we've designed our PID controller. And remember that we're looking for no steady state error for a step input. So over here I've copied across my table, which is able to tell me the steady state error that I get for each type of input, so step, ramp, and parabolic. So we just discussed that we have a type 1 system, so that's this row here. And we're interested in a step input, so that's this one here. So this is the cell that we're interested in, and we can see that no matter what we do, we're always going to get a steady state error of 0 for a step input and a type 1 system. So that means that just by designing a PID controller, no matter what, we're going to ensure that we have no steady state error in our system. So this third criteria here, we've already pretty much met it by going through this process. So now we just need to focus on making sure that we get our settling time and overshoot to be what we want. So that concludes step 1 pretty much. We've decided on our desired pole locations. So the next step that we need to follow through with is finding where a 0 would need to be placed in order to get the desired poles on the root locus. So there's two different methods that we can use. I'm going to go with this one here, which is the more graphical method, but either one will work. Alright, so let's draw ourselves a little root locus diagram. We're not going to do the whole thing, but we're just going to mark a few key points. So the first thing I'm going to mark is our desired poles. So we've got 2 since it's a second order system. So let's say that out here somewhere is -40, and the height here is going to be 42 and -42 for those 2 poles. So these are the desired, I'm going to put closed loop poles. So the other ones that I'm going to place on here is we're going to be interested in where our open poles and zeros lie. So if we go back to our transfer function that we had, our open one, alright, we said it was equal to 10, which doesn't really help us for the root locus diagram, divided by s plus 1, s plus 2. So that means we're going to have open loop poles at, from here we get one at -1, and from here we get one at -2. So let's go with that for now and mark them down here. So they're going to be very close to the axis. So -1, -2. Now what we're doing through this first bit where we're placing a 0 is we're designing the PD controller. So the PD part of what we've got here relates to the Ks plus A in the equation. This relates to like the D, and the K here relates to like the P. So let me write it out and make it a bit more sense. So PD. Okay. So this is the P, the proportional bit, and this is the D for the differentiator bit. So we're introducing an A, or 0, sorry, this is going to be at -A. Alright, so let's draw this onto our diagram as well. So we're not really sure exactly where this is going to be, so we can kind of just make a guess at it. So I'm going to say, okay, I'm going to guess it's out here. Oop, should draw it as a circle since it's a 0. And it's going to be at some position -A that we need to work out. So the equation that we need to satisfy is that the sum of the 0 angles minus the sum of the pole angles has to equal -180 degrees. So if we satisfy this equation, that's going to mean that these 2 desired closed loop poles are actually sitting on our root locus, and therefore we're going to be actually able to get our system to respond in the way that we want. So let's mark in our angles that we need to use in this equation. So I'm going to call the angle between negative A and this desired pole theta 1. And we're going to have two angles out here. Okay, now these need to be measured from the positive real axis anti-clockwise. So that's going to mean this angle in here, I'll call it theta 3, and this angle in here is the one we're interested in, I'll call it theta 2. So let's substitute into this equation the theta 1, 2 and 3 that we've just put on the diagram. So this one relates to the zeros, and this is the 0. This is going to be theta 1. And then we have 2 that we need to sum in here. We've got theta 2 and theta 3, which relate to the poles. Alright, so we can go through and figure out what each of these angles is. It's just going to be regular trig. So let's start with theta 2, I think. That's going to be the easier one. So if we want the angle that's from the positive real axis around to this line here, what I'm going to do is take 180 degrees, which is the angle in a straight line, and I'm going to take away this little piece in here, which will leave me with the other side. So I can get the little piece by taking tan inverse and looking at the triangle that sits in here of opposite over adjacent. So the opposite side is this one, it's going to be 42, and the adjacent side is this one in here. So it's going to be the difference between 40 and 2, which is 38. And this is going to end up with 132.14 degrees. And I should mention, it doesn't matter whether you pick this pole to do your calculations on or this pole to do your calculations on. You should get the same values. You just need to, pick either one. Doesn't matter. Alright, so the next one I'll go for is theta 3. And I'm going to use the same kind of method. I'm going to take 180 degrees, which is the number of degrees in a straight line, and then minus away the piece in here. So again, I can use tan inverse of the opposite, which is still going to be this height of 42. And the adjacent this time is going to be the difference between 40 and 1, which is 39. So this one we end up with an angle of 132.88 degrees. And the last one that we need to do is theta 1. So again, we can apply the same kind of method. This time I don't need to do the 180 minus thing, because I just can get this one in here straight away by doing my tan inverse. So the opposite side is going to be the height of the triangle here, which is 42. And the distance in here is going to be A, wherever my 0 needs to be, minus whatever distance, which is 40. So there's not much more I can do at this point to simplify that. So what I'm going to do is take all three angles that I've just simplified and put them back into this equation here. So one, 4. So now I just need to go through and solve for A, which is the only unknown in the equation. So I'm going to shift this over to the other side, which will give me 85.02. And then what I'm going to do is undo this tan. So it's a tan inverse. To undo it, I can just, I'm going to put this here, which is what's inside the bracket, and put this to the other side, and it goes from tan inverse to tan. Alright, so now I need to get this A on the top line. So I'm going to divide by tan. And at the same time, I'm going to multiply this up. So A is just going to be this plus the 40. And it ends up coming to 43.66. So this is where the 0 needs to go. So if I come back up here, get rid of this for a moment, this is equal to negative 43.66. Okay. Alright, so let's just look for a moment what we've done since we have access to MATLAB. So I've written a code which is able to plot what we're doing. So this is the first bit where I've just set up my system, and I'm just plotting directly the root locus that I would get if I had that system. And this would represent designing just a gain controller for it, if we just picked a value of this diagram. And what we can see is that we have our open loop poles at -1 and -2, but remember that our desired poles were well, out here somewhere at -40 plus or minus 42i. So in this first instance, there's absolutely no position that we could pick on these root locus lines in order to achieve those desired poles. So that's why we've gone ahead and put in this 0. Okay, and that's what the second part of this code is doing. It's looking at, okay, let's design it now with a 0 at -a, and I've set that to 43.66, which is what we calculated a moment ago. And this is the new root locus diagram that we can produce. So we've still got these open poles down here at -1 and -2, and now we've introduced this extra 0 into our system. So I'm going to go through and just see if we can actually identify that our point of -40 plus or minus 42 actually lies on the diagram. Alright, so this is a little bit dodgy. It doesn't pick up every point, so this is probably the closest we're going to get to it with the dot to dot points that we can select. So it's about -40 plus or minus 42. Alright, this would be one pole, the other one would be down here reflected along that x-axis. And you can see that now we do have the potential to actually pick up on this point and design our controller. So then that's what the next step now represents, is figuring out what value of k for the gain do we need such that we're sitting on this point. Okay, and you can see here that it should be about 8 that we should be able to calculate manually. So let's jump back now to our calculations, and we're going to go through and try and find this point. Let me just remind you that if you're following through on this method, this is now step 3, finding what gain the desired pole needs to have. Going with this graphical method, but equally you can use this other method here as well. So for the graphical method, we're going to be looking at the lengths of poles and zeros. So that's the line that we can draw between, say in this case, our 0 and our desired pole. So let's call this one L1. This one in here I'll call L2, and this one I'll call L3. So the equation that we need to fill in is that the overall gain in our system is equal to, this pi is actually the product symbol, so multiplying things together, just like this one here is like the sum of symbols, so you add things together. So we need to multiply the pole lengths, and on the bottom line we need to multiply the 0 lengths. So if we replace it with what we've got in terms of L1, L2 and L3, the length of the poles, we've got these two, so it's going to be L2 times L3, and we've only got one 0 which we've called L1. So again we need to go through and figure out what these values are, and we should be able to do this using Pythagoras theorem. So let's start with L2. So if we apply Pythagoras theorem, what we're looking for is this is going to be the hypotenuse. Alright, we've got a vertical length and a horizontal length in here that we need to put inside the square root. So this length in here is going to be 42, and this length in here is going to be the difference between 40 and 2, which is 38. So we end up with a pole length here of 42.16. The next one, we'll go with L3. So using Pythagoras theorem, the height in here is 42, and the length in here is going to be 40 minus 1, so 39. So this one ends up having a length of 57.31, and I've just realized I copied the wrong one here. So this actually, sorry, was 56.64. So now we should be able to do L1, which is this length in here. The height again is 42. And the width in here is going to be the difference between 43.66 and 40. So that's just 3.66. And this is the one that comes out to 42.16. So now we should be able to go back and put these three numbers into our equation for the overall gain in our system. So 56 times 57 on 42.16. And we end up with an overall gain of about 77. So the reason I've called this overall is because if we look back in our original transfer function, all right, up here, the open one that we've got written out will do, we can see that on the top line of our transfer function, we've got an existing gain of 10, which came from like the plant or the system that we had here. Plus, we've also got the gain k that we need to design, which is the one that comes from our controller transfer function. So at the moment, remember we're designing just the PD part. So yeah, this k in here. So all we need to do is take the overall gain from our system, which was the 10, and the k from the controller, and figure out just what k on its own needs to be. So it's going to be 77 on 10, which is about 7.7. So that means that the PD part of our controller, which was ks plus a, is going to be 7.7 s plus 43.66. So that now concludes step 3 of our procedure. And if we want to, we can just double check from before. We saw that using our MATLAB tools, we should be aiming for a gain of around 8 for our poles to actually be sitting on the root locus and selecting that desired location. And we pretty much got that with 7.7. There's not too big a difference there. That definitely confirms that we're on the right track. So, jumping back to our method, we're now up to the part where we design the PI part of our controller. And this is the part that's going to eliminate the steady state error. That's because we're introducing an extra integrator, which is the pole at 0. So the first thing that we need to do here is add that pole at the origin or at 0. Then we're going to end up choosing a 0 position that's very close to the origin, and this is such that we achieve pole 0 cancellation. So we don't want to modify our root locus diagram at all, because we know that we can actually achieve the desired pole that we were looking for. We want to keep it exactly how it is, just with this extra pole at the origin and extra 0 near the origin such that they cancel out. So jumping back, so we're designing the PI part of our controller, which means now that our controller is going to look like a PID. Okay, so we're still keeping this part from what we just designed, that's this bit. We're just introducing the S plus B and the S. So this is our pole at the origin, okay, on 0. This here is now going to be an extra 0 that we introduce at negative B. So you have a bit of control over where you want to put the 0. This is because if you're using a manual method, you're not going to really be able to check the effect that it has. You're only going to be able to do that if you have MATLAB or something else that can simulate for you. So if this is an exam, you just have the option to pick a small number. So let's say I let B equal, I don't know, negative 0.1. We should be able to now sub that in to our controller transfer function, and it will be complete. Sorry, this was 43.66. Alright, so that's my PID controller that I've chosen to design. And what I should find is that I end up with pole 0 cancellation because I have a 0 at negative 0.1 and a 0 at 0. So these are very close to each other, so it should have a very minimal impact on the root locus. So let's say I simulate now with my 0.1 inside my controller now. So this is the complete one. Plot the root locus. This is what I get. So what we can see is that we have still got our two open loop poles at -1 and -2. We have our 0 that we introduced at about 43. And what we've got right near the origin now is going to be a pole at 0 and a 0 at -0.1. So let's zoom in and have a look at that. Alright, so that's what we can see definitely. Yeah, that's the pole at 0, that's the 0 at -0.1, and these were our open loop ones. And you can see if I zoom back out, the shape of this root locus diagram is awfully similar to what we had a moment ago when we just had the PD part. Okay, there's almost no change in the shape of it, and we should still have our closed loop pole, desired one, in a pretty much exactly the same location because they've just cancelled each other out. So let's just say for a moment I picked a bigger number, which would mean that we have less of that pole 0 cancellation. Let's say I pick b is equal to 5. What we should find is that we will see a bit of a change in the root locus diagram between what we had before and what we had after. Alright, so this was the before, this is the after. So you can see now that there's like a little bit of change that's happening here. So it might not be that substantial to affect the closed loop pole all that much still. But I don't know, let's say we push it even more and make it like 10 or something like that. And have a look at what the change is. You can see that this one, yeah, definitely looks not so good. Yeah, it's starting to bulge more and more around these points, which means that we're also probably getting a bit of an impact up here. So our desired pole may not necessarily sit on our root locus anymore. So yeah, we haven't really achieved that pole 0 cancellation that we were looking for. So yeah, I'm going to go back to my point 1. That looked okay. Didn't really have too much of a difference for the two root locus diagrams before and after inserting that extra I part. So yeah. And just remember that if you're in an exam, you don't really have the opportunity to check that. So just pick a small number and say that you assume that pole 0 cancellation occurs. So all that's left now is probably for us to just double check whether our criteria have actually been met for our simulated result. And again, you don't really have the opportunity to do this unless you have access to something like MATLAB to be able to simulate your result. So I'm going to put this controller that we designed into MATLAB and we'll simulate the closed loop response. So this is me just putting in the K value that we chose, setting up our transfer function, making sure we close the loop, and then plotting the step response. So this here is the response that MATLAB gives us. So what we were interested in was our criteria were for settling time and overshoot way back at the beginning. So let's have a look. So remember that we were aiming for an overshoot of 5%. And we can see here that we've got 19.9%. So obviously that's quite a lot bigger than what we were aiming for. And I'll talk about the reasons for that in a moment. And the settling time we were aiming for was about 0.1 seconds. So you can see here we've got 0.08, which that's probably quite close to what we were aiming for. And again, we can discuss the differences in a moment. We also had that criteria about steady state error, but we said that as long as we designed our PID controller, we should end up with 0 steady state error. So we can see here that I put in a unit step, so that means that we would expect that the response should be 1, and we can see that we've definitely got this final value of 1. So that would suggest again that we've achieved that steady state error requirement. Alright, so I've written a list of our criteria versus the aim that we were going for versus what we actually achieved. And I'm just going to quickly run us through why we got some differences. So for the settling time, we got a value that was slightly less than what we were aiming for. And probably the main reason for this was the approximation formula that we used for the settling time. So remember that this one here, okay, that we use way back up at the beginning to figure out what our natural frequency should be, is an approximation. So as a result, you're going to introduce a little bit of error from that. So the next one is the percent overshoot, and we saw that we had quite a big difference here. So the main reason for that is because we introduced zeros. And we had two of them, okay? One we introduced at negative, it was 43.66, and the other one I chose to put at negative 0.1. So the effect of introducing zeros means that you increase your overshoot. And this was not accounted for in our theoretical equations or analysis. Oop. Okay, all of our analysis was done based on the fact that we had no zeros back at the beginning. Remember that again we did our calculation for our desired poles should be based on this damping ratio and omega n. And at this point we're assuming that we had no zeros in our equation. So as a result, we've got quite a bit of error introduced there. The other thing that you can look at for this is the effect of dominance. So if I go and have a look at where my closed loop poles and zeros are for my designed system, these are the two desired ones that we were going for. These two here were meant to have pole zero cancellation, and this one out here was the extra one we introduced. So remember that the closer a pole or a zero, doesn't matter which one actually, is to the imaginary axis, the more effect that it's going to have. So these two are supposed to cancel each other out, so they shouldn't have too much. But this one here, it's at kind of like a very similar distance to what our closed loop poles are at. So therefore, it's probably having quite a big impact on our response, which would explain why we got much higher overshoot than what we were aiming for. All right, so they're dominant in the response. Can't be neglected. The last one was our steady state error for the step. We saw that we actually achieved our aim perfectly, so obviously we don't need to account for the difference there. So that's all there is for this video, and I'll see you in another one.